Hey everybody, welcome back. This is solving trig equations, the next lesson. In this lesson, even though we are still solving on the entire unit circle from 0 to 2 pi included, we're going to be using some examples that have identities to use, not just reciprocal, but we're going to tuck in the Pythagorean identities, the double angle identities. We can see sum and difference identities, and we could also see the half angle identities. Those are going to be the focus of today's lesson. So our first example is 2 sine of x minus sine of 2x equals 0. So in this case, we do have a 2 in front of the first term, and then we have a 2 in front of the x for the second term. So that right there means that we are doubling that particular angle. So we want to use the double angle formula in order to be able to solve this equation. So quick check, sine of 2x equals 2 multiplied by sine of x multiplied by cosine of x. So we are just going to take that value of the double angle and replace the second term with its value. So we have 2 sine of x for the first term minus formula, or the value of sine of 2x, which is 2 sine of x cosine of x, and all of that is equal to 0. So from this point on, now we're back to our regular problems that we've been doing for quite some time in the previous lessons, where we're going to look for a greatest common factor. We're going to see if we can solve by taking the square root or factoring a difference of squares, or if we have a trinomial that we need to factor like we factor our quadratics. So this one has a GCF. We have 2 sine of x in both first and second terms. So I'm going to factor that common factor out. Remember, it's kind of like dividing. It is just like dividing. It's basically you're dividing that term out of the terms that you're given. And then you write what's left over. 2 sine of x divided by itself is 1. Negative 2 sine of x cosine of x divided by 2 sine of x is a negative cosine of x. Now those two factors are multiplied together and set equal to 0, so you can now separately set them equal to 0 and solve. So 2 sine of x equals 0, divide both sides of the equation by 2, so sine of x equals 0, and when we take the inverse, sine inverse of 0, we're looking for those radians or degrees around the unit circle where the y value is 0. That occurs at 0 radians, pi, and at 2 pi. Perfect. Now if we solve the other factor, our second factor that we have is 1 minus cosine of x equals 0. We will isolate cosine, so we get cosine of x to equal 1, and when we do cosine inverse of 1, we're determining where do the x values on the unit circle equal positive 1. Okay, well, yeah, that's at 0 and at 2 pi. So yes, we do have repeat answers. 0 and 2 pi are true for both of the factors. You only have to list 0 pi and 2 pi as the solutions, but you should still show the work for solving even though the cosine factor gave us the same values. Okay. All right, next example, number 2. Cosine of 2x equals 1. Well, lo and behold, it's the same type of problem, except now it's cosine of a double angle. So the double angle formula for cosine is cosine squared of the angle minus sine squared of the angle. Okay, so we can just straight up replace cosine of 2x with cosine squared of x minus sine squared of x and set it equal to 1. Now in this case, we've kind of made a little bit bigger of a mess because now I have 2 trig functions within that entire equation. So what we're going to have to do is use a different identity to help us get back to just having one term. So another identity is a Pythagorean identity. Sine squared plus cosine squared will equal 1. So our choice, it's whichever you choose. You can isolate the cosine squared term in the equation, or you can isolate the sine squared term in the equation. It truly doesn't matter. Okay, it's not the only way to do it, it's just the way that I see to do it. I'm going to isolate cosine squared because that one's first and positive. So cosine squared of x would be equal to 1 minus sine squared of x. So I can replace that first term, cosine squared, with 1 minus sine squared, and then that is still multiplied, or excuse me, and then I still have minus sine squared of x equal to 1. Now at this step of the game, we can combine all of our terms and we can work through the process in order to isolate the sine squared terms. So a negative sine squared minus sine squared would give us negative 2 sine squared. So I have 1 minus 2 sine squared equals 1. If I subtract 1 from both sides of the equation, I'm left with negative 2 sine squared of x equals 0. When you divide by negative 2, you will now have sine squared of x equals 0. And when we take the square root, yes, we're supposed to get positive and negative values, but the square root of 0 is 0. So we just have sine of x equaling 0. Now, we've already solved for that. We know that the y value equals 0 at 0, pi, and 2 pi. Okay, so that was good work using two different identities and having to take a square root. Yay us. All right, let's try number 3. Number 3 is cosine of x equals secant of x. Okay, we've got two different trig expressions. Yes, I can rewrite secant, so we can do that. I'm also going to go ahead and subtract the secant to the other side of the equation to set it all equal to 0, and then I'll use the reciprocal identity. So cosine of x minus 1 over cosine of x is now equal to 0. Okay, again, we keep making a bigger mess, but we're going to get through it. Get a common denominator. Cosine has a denominator of 1. It needs a denominator of cosine in order to combine those two fractions together. So we will write this as cosine squared over cosine of x minus 1 over cosine of x all equals 0. Okay? Now, you could skip that step and jump straight to writing it as one fraction. Cosine squared of x minus 1 all over cosine of x equal to 0. And now we can get the trig function by itself so that we can solve. Okay, so we have cosine squared of x minus 1 all over cosine of x equals 0. You can solve it just like it is, or if you want, you could use a Pythagorean identity if you choose to, but you can still solve it. Remember, any number, unless it's already, well, even with fractions, but any number is going to have a denominator of 1, so I can really cross multiply. Cosine squared of x minus 1 multiplied by 1 equals cosine of x multiplied by 0. Okay, so that just means cosine squared of x minus 1 equals 0, and now when we isolate to get cosine by itself, we'll add 1 to both sides of the equation and take the square root. Cosine of x will now equal both positive and negative 1. So where does cosine equal both positive and negative 1? It's positive at 0, it's negative 1 at pi, and it's positive 1 at 2 pi. That is not the only way to solve this. You could have, again, done a replacement of a Pythagorean theorem with the cosine squared minus 1 term and still ended up with the same solution. Okay, moving along. Number 4, secant squared of x minus 2 tangent of x. Okay, we have a couple of choices, so let's look at what we have before we make a final decision. I know that secant is 1 over cosine, so secant squared would be 1 over cosine squared. And tangent is sine over cosine, so that would be 2 multiplied by sine and then divided by cosine. Okay, so we can kind of make those have the same denominator to begin with. We could try to do that and see what kind of solutions that we get. Another option is there is a Pythagorean identity that tangent squared of x plus 1 equals secant squared. So I could just replace the secant squared with tangent squared of x plus 1 and see where that gets me. I think I have time. I'll go ahead and do this one both ways so we can kind of decide which way we like best. So let's do 1 over cosine squared of x equals 2 sine of x over cosine of x. Okay. So what we could do is, if I multiply the second fraction by cosine in numerator and denominator, then I'll have 1 over cosine squared equals 2 sine of x cosine of x all over cosine squared. Now, if you have two fractions set equal to each other that have the same denominator, when you cross multiply, you will end up eliminating that denominator. I'll prove it to you. Here goes. 1 multiplied by cosine squared is cosine squared. That's equal to cosine squared multiplied by 2 sine of x cosine of x. Okay, so if I were to then divide through by cosine squared, then that term is now gone. So I get 1 equals 2 sine of x cosine of x. Okay, we could put that back in terms of the double angle formula because that is sine of 2x, but we've got to know how to solve the problems with double angle formulas. So at this point, there's no way just to purely isolate sine or cosine. And you kind of get stuck unless you know how to solve with the double angle, okay? So not wrong, you would have some extra steps to go with that one. Let's start the other way and see if we can get through this one. So we are going to replace secant squared of x with tangent squared of x plus 1, and that is equal to 2 tangent of x. I think that this might be a better route for most of us because we're pretty good at factoring. That's right. We're going to subtract that 2 tangent of x to the other side of the equation and put it in between the terms so that it'll represent what a quadratic would look like. Okay, so if I change tangent just to be x's, that would be an x squared minus a 2x plus 1, and we know how to factor that for sure. What multiplies to 1 and adds to negative 2? That's right, negative 1 and negative 1. So if I know my factors in terms of a quadratic are x minus 1 quantity squared or x minus 1 multiplied by itself, I can change these factors in terms of tangent to be tangent of x minus 1 multiplied by tangent of x minus 1. And again, you could write that as tangent of x minus 1, the quantity squared, equal to 0. Whichever way, it doesn't matter. You're still going to solve by setting tangent of x minus 1 equaling to 0, add 1 to each side, and then when you take the inverse, you determine where does tangent equal positive 1. It's positive in quadrants 1 and 3, and it equals 1 at the pi over 4 radians. So at pi over 4 in quadrant 1, and then in quadrant 3, that's going to be 5 pi over 4. Okay, that is going to be it for these first 4 examples. I'll come back with another video for examples 5 through 8.